Hi, welcome to my channel. So in this video, we'll discuss about the strains which are created by the external loads in a material, right? So before going into our video, we'll do the recap of the last class. So we discussed about the stress, the definition of stress. We talked about definition of stress. What are the different types of stresses, right? So stress is the resistance offered by the material to the deformation caused by the external load, right? The stress can be measured in two types. One is total stress and another one is unit stress. Total stress is the one which can be measured in terms of Newton or kilonewton or meganewton. So unit stress is the stress which resistance which is measured per unit area, right? So that is why this unit stress unit is Newton per mm square or kilonewton per meter square or meganewton per meter square. So there are different types of stresses based on their application. One is direct stress and another one is indirect stress. So direct stresses are tensile stress, compressive stress and shear stress. And indirect stresses are bending and torsion. So in a material, any combination of stresses can occur, direct stress and indirect stress, right? So here we have applied a load P amount of load, tensile load, and we have measured the cross sectional area. So the stress can be referred by the letter sigma, and the sigma is P divided by A. Right. Now we'll talk about the strain. So strain can be defined as the deformation which is produced by the external load. So we can say that any body subjected to stress can be called a strain. So that we can call that material as a strained material. So what are the types of strain? So depending upon the types of stress, we can name the corresponding strain. Suppose a material is acted upon by some tensile load and the stress calculated is tensile stress and the corresponding strain is tensile strain. Likewise, we have compressive strain, shear strain and volumetric strain. So we are applying direct compressive axial direct compressive force, right? And we are measuring the strain, means that particular strain can be called as compressive strain, right? The shear force is applied, so the deformation which is caused by the shear stress can be called as a shear strain, right? So volumetric strain is the change in the volume, so deformation is caused to the overall body, so that can be called as volumetric strain. So how can we measure the strain mathematically? So mathematically, strain can be measured as the fractional deformation. So what is fractional deformation? Change in the ratio between change in the dimension to the original dimension. Or else, in general, the students can remember the strain as the definition of strain as change in length to the original length. So tensile strain, right? So what is tensile strain? So consider this rod, and this rod is acted upon by some external load P, and this rod has a cross section of square, right? I am applying the tensile load. Because of the action of this tensile force, there is the deformation. That is, deformation here is change in length. So the load deformation is del L. So the final length after the deformation is L plus del L. So how can we measure? We can obviously say that this material is a strained material. It's strained. So how can we measure this strain? So strain can be represented by the letters E, small e, which is equal to change in length divided by the original length. So how much length is changed? So del L is the change in length and L is the original length. So your formula will be del L divided by L. Likewise, we have compressive strain. So when a material is acted upon by compressive force, right, what happen? Obviously, the length of the material will reduce. So that reduction in length can be called as deformation caused by the external load. Right? So the amount of reduced length is del L. So change in length is del L. So how can we measure this tensile strain? As usual, strain can be defined as change in the dimension divided by original dimension. So what is the dimension changed here? Length. So change in length divided by original length is the formula for compressive strain. So change in length is del L and original length is L. Right? So formula is del L by L. So coming to the shear strain. So, to understand the shear strain, consider a two-dimensional element like this, a rectangular box, which is fixed at this end, at this edge OP, right? And it is free to move or at the edge N and M. Nm, right? I am applying some horizontal force of amount P, right? Because of the action of the force, what happens? The rectangular shape of the material changes to the parallelopiped one. So this position of N changes to N dash and position of M changes to M dash, right? So the angle of deformation is phi. So the shear strain is how much this edge ON has moved, right? So this is the shear strain. So how can we measure this angle? By taking tan phi, right? Tan phi is equal to opposite divided by adjacent. Opposite is N dash divided by ON. Or else we can measure this side of the angle over this side, right? So tan phi is equal to M dash divided by MP. Right, so this is since the angle will be very low, so tan phi can be taken as phi, right? So phi is equal to N dash divided by ON or M dash divided by MP. So this is shear strain. So volumetric strain is the change in the volume of the body. So how can we measure the volumetric strain mathematically? Is that by taking a ratio between change in volume to the original volume. So del V divided by V is the formula to calculate volumetric strain, right? So next we need to discuss is elasticity and elastic limit. Right? So whenever a body is subjected to external force, it undergoes deformation. On the removal of load, the body comes back to its original shape or size or position. The body comes back to its original shape or size on the removal of the external load is called elastic body, and the property of returning to the original shape or size can be called as elasticity. Right? If the body does not come back to its original position even after the removal of external load, then that particular body can be called as plastic. Right? So from this we can observe that there is always a limiting value of load up to which the strains disappear on the removal of load. The corresponding stress can be called as elastic stress, and that corresponding load can be called as elastic limit. So while discussing elasticity and elastic limit, we should also discuss about Hooke's law. So Robert Hooke discovered experimentally that within elastic limit, stress varies directly as strain. So this constant is termed as modulus of elasticity. So stress is directly proportional to strain. Stress divided by strain is equal to a constant. So this constant can be called as modulus of elasticity. For a material, we have three modulus of elasticity. One is Young's modulus, and another one is bulk modulus, and another one is shear modulus. So now we will discuss about, we'll look upon this Young's modulus now. So Young's modulus can be defined as the ratio between tensile stress to the tensile strain or compressive stress to the compressive strain. So tensile stress can be represented by sigma T and compressive stress can be represented by sigma C. Tensile stress can be represented by ET and compressive strain can be represented by EC. So sigma is Young's modulus or modulus of elasticity. This Young's modulus can be called as modulus of elasticity. So modulus of elasticity is equal to tensile stress divided by tensile strain or compressive stress divided by compressive strain. So whenever you do the analysis of any material, right, or you do analytical or experimental, you do the analytical analysis, or you adopt experimental method for the analysis of any material, you should need this Young's modulus property. So Young's modulus of the material is very important property to predict the behavior of the material under the action of external force. So it specifies the material that how much it can extend under the action of tension or shortens under the action of compression. So next we need to discuss is modulus of rigidity, or it can be called as shear modulus of elasticity. So you might have got some idea. So how we can define modulus of rigidity or shear modulus of elasticity. So which is equal to shear stress divided by shear strain. So this this modulus of rigidity can be represented by the symbol C, N or G. You can use any of these letters, right? So tau is the shear stress and ES is the shear strain. So tau divided by ES. right? A large shear modulus value for a material denotes that that particular material is highly rigid. Next, we need to discuss is bulk modulus, or that can be called as volume modulus of elasticity. So bulk modulus can be represented by the letter K, capital K. So capital K is equal to sigma n divided by EV. Sigma n represents direct stress, EV represents volumetric strain. So we have already discussed the volumetric strain. So volumetric strain is the ratio between change in volume to the original volume. So next we need to discuss is stress strain curve. So this stress strain curve is for mild steel material, right? So whenever this mild steel material is subjected to some external load, say it is subjected to tensile force, right? So at the very start, you can observe stress increases and strain also increases. So there is a linear relationship between stress and strain. So the increase in the stress strain curve is linear and is proportional to stress and strain. So up to this point, right, stress and strain are not proportional. Beyond this A point, stress and strain are not proportional. So this A point can be called as proportional limit, and it reaches a point B where elastic deformation start to set, right? So, and as the load increases, the strain capacity of the material reduces at the same, stress capacity of the load carrying capacity of the material reduces, and at the same time the strain increases. So it reaches further point which is called a lower yield point where the permanent deformation start to set. Right? On the on further application of the load, what happens? The stress capacity also increases, and the strain more than the strain value increases, which represents it deforms more under the action of the load, where it reaches a certain point where necking of the material happens. So necking is the reduction in the dimension of the material. So beyond this point, if we apply continuously load, what happens? Breaking of the material happens. So this E point represents breaking of the material, and D point represents ultimate strength of the material. E point represents yield strength of the material. So this upper yield limit will not be considered for the calculation, because this upper yield limit is just a momentary value. Right? So you can observe in this curve, on the very start of the test, what happens? The material capacity increases as stress is directly proportional to strain. At a certain point, what happens? The material capacity reduces. But after that, what happens? The material capacity increases. Right? On the further application of the load, material capacity increases. So this property is called as strain hardening. After the permanent deformation has set and we apply the further load, right, what happens? The capacity of the material increases, which is clearly depicted by this plot, a stress strain curve, right? And this portion is called as strain hardening, right? Because the molecules in the material rearranges to the new position, which increases the load carrying capacity of the material even after the permanent deformation. Right? So it reaches a certain point where it cannot carry any further load. So this is where the necking of the material happens, and the further application of the load causes breaking of the material. Likewise, we can have typical stress strain curves for different types of materials. Right, highly rigid material, elastic material, mild steel material. For different types of materials, we can have different profiles of stress strain curve. Upper yield limit corresponds to the load that is required to initiate yielding. Lower yield point corresponds to the minimum load that is required to maintain the yield. Normally, we use lower yield point to determine the yield strength of the material being tested, because the upper yield is momentary. So we'll discuss this problem in the next class, okay, in the next video. Until then, thank you. Bye-bye.